Dun, 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 dun. Hello. All right. Go ahead and get started. Today, we're gonna change gears a little bit. I will backtrack a little bit to talk about some of the trust things that we were doing last week, and then we're gonna move to this completely new theme that you've never heard of, strong forms and weak forms. So let's go ahead and get started. A little bit of where this is going in the next and how it connects with the book. What we're going to talk about today and on Wednesday is this idea of going from the strong form to the weak form. We'll talk about what that means. So that's basically this week. Then later on, we're gonna, I think starting next week, we're gonna start with approximation of functions. And we're actually gonna introduce the concept of finite elements and finite element interpolation. So this is gonna be for next week, but this is where we're gonna talk about finite element interpolation. And then when we combine both of those, then we're gonna get to the discrete equations for the elasticity problem and the heat transfer problem. What we did in the last week, we already were here. So this is basically where we were last week already. So we already know a little bit of this. From trusses. Actually, the reason why we started with the trusses is because it was a good way to start with a system that is already a discrete system. You already have just sum of forces, you have well-defined elements. And then just to get a little bit familiar with this idea of giving an element equation, how to assemble that into the global system of equations and how to solve that. So that's why we started there. But in reality, to apply the solution and to have this discrete set of equations for things like heat transfer or stress analysis, we need these other two components that we haven't talked about. We need this a little bit more theoretical part, which is the strong form to weak form. It's a little bit more math. And then we need this other part of discretization. So how do you represent functions with the finite elements? So that's what we're gonna be doing in the next couple of weeks. And then you'll see in like 3 weeks or so, when we put those two together, we're gonna have something that looks very similar to what we did for the trusses. So just a recap, I'll make an extra note here. Just to say what we were doing for trusses. Because we'll come back to this, it's gonna be the same structure even when it's not trusses. We have obviously some mesh, which consists of both the nodes, coordinates, and the element connectivity. We have an element equation. Which we are going to express for any type of problem is going to look something like this, where obviously it does not necessarily have to represent displacements and forces. For trusses, it was like that, but this will generalize for all the problems. It's going to be some matrix times some degrees of freedom. You can think it, like I said, for trusses is displacement, but you can think of this as degrees of freedom. This could be temperature. This could be displacements. This we call the stiffness matrix. Even when it's not stiffness matrix, we're going to have a matrix that basically relates the displacements or the degrees of freedom to some forces. And again, I'm putting it in quotation because it is forces for the trusses, but for heat transfer, this is actually fluxes, for example, the heat flux. But it has the same structure. And then there's an assembly process. And then we're gonna, and this again, this repeats over and over and over again. We're gonna have this global stiffness matrix. And the assembly process is the same. We have this global stiffness matrix, we have the global degrees of freedom. And that equals always to some unknown reactions. I should say here, in this form, it's global degrees of freedom plus nodes with known degree of freedom, or nodes with boundary condition. These are external forces. And once we assemble this global system of equations, then we cannot solve that directly because we have sort of a mix of unknowns and knowns in the left and right hand side. So the vector U, for example, contains some nodes for which we actually know the displacements, the degrees of freedom, and also some for which we don't know the displacements. And then the right hand side has some known components, all the external forces we know, but it also has some unknown reactions. So here there's a solution of that system of equations. And then similarly to what we did for trusses, mainly two techniques, either split the system using block matrices, or this one, which I don't really do, which is replace equations with trivial equations. So there's the two, but preferred one is this one. Again, so this is sort of a recap of what we did for the trusses, and I just want to put it here because, like I said, this is just going to come up over and over again. All right, so what we are going to do today is actually a step that goes before any of this. It goes before this, what we're going to do today, because it's basically for the equations of heat transfer and stress analysis, we cannot really use them the way they are. And so we need to massage the equations a little bit to get them in a form that then we can use to get this element equation. So that's what we're gonna do today. So what is the so-called strong form of linear elasticity? This is in the book. But essentially is a PDE in this format. And again, I will make distinction for why this is a strong form, but this I would describe as your classical PDE problem. This is the way you have seen things in, for example, Math 303, right? So you get an equation that you need to solve. So you need the PDE to solve. So in this case, the derivative, it's going to be the second derivative of the displacement plus some b over some domain. For example, solve that PDE for x between 0 and L with two types of boundary conditions. You either get, these are called several names, either derivative boundary condition, also called Neumann boundary condition, also called natural boundary condition. And specifically for stress analysis, this is called a traction boundary condition, because what you are told is basically the stress at the boundary. The derivative boundary condition, why is it called derivative boundary condition? Because you know something about the derivative at the boundary. So that makes sense, that it will be a derivative boundary condition. Why is it called Neumann boundary condition? Just, I don't know, some guy that was the one that formulated it or called it a Neumann boundary condition. Natural boundary condition, this one is actually related to the to this strong form to weak form, and this we'll talk about. So this is related to strong to weak form process. That's actually why it's called natural boundary condition, as part of this, how you go from the strong to weak form. And traction boundary condition, because by prescribing something related to the derivative of the displacement, actually what you are prescribing is some force or some traction. Force with traction. The technical name is traction rather than force, because in principle we can only define sort of pressure loads, so things that have units of stress. So it's not really, it's always traction, not really force, but stress is just force per area. So if you know the area, you can also say it's a force boundary condition. So that's one type of that boundary condition. And then the other type of boundary condition is a displacement boundary condition, obviously, as opposed to force. If you know the displacement, then it's called a displacement boundary condition. This is also called Dirichlet boundary condition, again, some person. I don't even know how to spell it, but I know it's pronounced Dirichlet. So Dirichlet boundary condition, displacement boundary condition. You can see that it's a boundary condition on the value of the function rather than the derivative. And then instead of natural, it's called essential boundary condition. And again, this essential boundary condition, that one actually is specifically related to the fact that we go from a strong form to a weak form. So lots of names for the same thing. And I'm guessing you have probably seen this equation before in 323, right? This is just stress analysis in one dimension. Actually, this guy right here, this inner part, that's stress. And the derivative of the stress plus B equals 0, that just means the continuum version of sum of forces equals 0. Like this. Yes. Good one. Put on the mic, didn't turn it off. Was something that I said not clear, not audible? Okay. Can you hear me now? Good. Other questions? Yes. Displacement is just that our degree of freedom is U, which is the displacement. So, Dirichlet. I I think it's spelled like this, but don't quote me on that. I would say Google. But I think if you put in this and boundary condition, I think Google will know how to spell it. It definitely sounds like Dirichlet. I think Neumann is correct. I think, is it spelled like that? Yes. Neumann, I think it is correctly spelled. All right, so let me do that. Let me do the process of strong form to weak form. It's kind of a recipe. So the first thing that we need to do is multiply by what we're gonna call test function and integrate. So we're gonna take our PDE and we're gonna integrate it. I'm gonna call it omega because that's just the general notation for the domain, but this is basically x from 0 to L of the equation, which is d dx AE du dx plus b. We're gonna multiply by this W of x, and that one is gonna be equal 0. We're gonna see what this W of x does. But for now, let's just follow the recipe. So if you have a PDE that has to be satisfied over some domain, integrate over the domain. Again, this integral, I'll just make a note, integral over omega. For the 1D case, for example, is integral from x equals 0 to x equals L. But the omega is a little bit more general in that if it was a 2D domain, the integral over omega would hide basically a double integral. Or if it was a volume, integral over omega would hide a triple integral. So it's just a way of saving space with that notation, integral over omega. So that's the first step. Then the second step is to do integration by parts on only for higher derivatives. And then this is passing a derivative from the unknown function to the test function. So I'm just gonna split the integral into two integrals. Just so that the integration by parts is clear. This is just standard things with integrals. You can always just split into the sum of multiple integrals. And you can see here that this is where we're gonna do integration by parts. That one you'll have to refresh a little bit of your calculus. But essentially, if you just remember sort of u dv, maybe I'll call it vdu so that it's a little bit vdu equals over some omega equals minus u dv plus integral over the boundary of uv. That's the integration by parts. So if we have something times the derivative of something over some volume or line or area, then it's going to be minus the integral, again, over the volume or the domain of just switch. Basically, you're passing a derivative from the u to the v, and then plus an integral over the boundary over the no derivatives. So in this case, we're going to get minus. So the thing that has the derivative, maybe I'll color code it. What is du is this thing right here. And v is the w. So I'm going to pass that derivative d dx that has this du. I'm going to pass that to the w. So I'm going to end up with d dx of the w. And then the other term was just the u, which is ae du dx. So again, really, I just passed this derivative basically from here to the w. And obviously, I changed the sign of my integral. But then I need to add an integral over the boundary of just the u and the v without this derivative. So that would just be a e du dx times w. And then the other integral is not affected. This is just b w of x equals 0. So just integration by parts. And then the third step is to use the boundary condition. Use boundary conditions. And then this you just have to know, but it's gonna look arbitrary, but it's if I know u of x on part of the boundary, then w of x equals 0 on that part of the boundary. So I'm gonna force that weight function or test function to be 0 whenever I know the displacement. And otherwise, if I don't know u boundary condition, then simply substitute the derivative boundary condition. So again, we have here an integral over the boundary that involves du dx, so the derivative of u, and it also involves the test function w. And then we have two cases depending on the boundary condition. If the boundary condition is that we know u, then for that boundary condition, we assign directly w equals 0. If the boundary condition is that we know the traction or the derivative, then we just substitute that. So let's do that. So we have integral of w of derivative of w of x times ae du dx plus, and now this integral I'm going to split into two. I'm going to split into part of the integral for which I know the displacements. I'm going to introduce more notation here. Typically, we use gamma u for that. I know a lot of notation, but let me scroll back a little bit. So typically, for example, here, I know gamma is usually used for derivative, for boundary, sorry. So So typically for domain, we use omega. Typically for boundaries, we either use partial omega to denote boundaries, or we use gamma to denote boundaries. And if we know the displacement, a convenient notation is to just say sub u, whereas for this boundary, this other boundary, we also either use partial omega or gamma, and then typically we use sub t, because what we know is the traction. All right, so going back to the integral, again, I have an integral over the boundary, and I'm gonna split it into two parts. I'm gonna integrate the part of the boundary where I know the displacement. And what I just said is that if I know the displacement, I'm gonna make this w of x be 0 in that part of the boundary. So I'm essentially gonna get rid of that integral. And then I have the other part of the integral, which is over the rest of the boundary, where I don't know the displacement, but I know the traction. For that one, I will keep my w, but instead of a e du dx, you can see that that's what I have for the boundary condition. So my boundary condition is that e du dx equals minus t. That's right here. So e du dx equals minus t. So here, I'm just gonna have minus area times traction. And then I still have integral over omega of b w of x. Equals 0. Okay, so just to recap, I had a PDE, which was the PDE that I need to solve over some domain with boundary conditions, two types of boundary conditions. Either I know the derivative or I know the actual function. So either I know something related to du dx or I know something related to u. They have different names. Don't worry about the specific names. How do we go from the strong form to weak form? We take that original PDE, we multiply it by some test function, also called weight function. And we integrate over the domain. Then you'll notice that the PDE obviously is a PDE, so it has derivatives. And then we're gonna do integration by parts in order to reduce the highest derivative. And integration by parts you can think of as sort of moving a derivative from one term to another term. So we did integration by parts. When we do integration by parts, what happens is that we end up with this boundary integral. And then when we have that boundary integral, we need to do something with the boundary conditions that we have. And then we just have two things to do. If the boundary condition is one of these displacement boundary conditions, then we automatically set the weight function to 0. If the boundary condition is on the derivative or the force, then we just substitute that value. And that's it. Now we can write the weak form. So I'll just say weak form is gonna be we wanna find the displacement on the domain omega that satisfies. So we are gonna require the essential boundary condition. So u of, in this case, L equals, I forgot what the value was. U of L equals U bar is the given value, but U bar. So find U of X on the domain omega that satisfies that boundary condition. such that this thing, let me copy, such that this equals 0 for all W of X with W of L equals 0. That is the weak form. So find U of X on the domain omega that satisfies this boundary condition of the displacement, such that that integral equation that we got is satisfied for all weight functions, with the only condition that the weight function has to be 0 whenever we have the displacement boundary condition. Any questions about the process? Yes. Yes.
For part of the integration, you have over omega and omega. The last thing you have delta omega is that.
Delta omega is the boundary. So usually the if you do in, for example, let me just show for 1D. For 1D problems, if you have integral from x equals 0 to x equals 1 of some function, let's say some function f of x times some function that looks like d dx of g of x dx. Let's say you have something like that. Then this would be equal to the integral, again, from x equals 0 to 1 of, and now I'm just going to pass the derivative. So g of x is going to stay like that, and then I'm going to have d dx of f of x dx, and then plus the an integral over the boundary. When you have a 1D, this is just evaluate on the edges of the domain. So this is just f of x, g of x, evaluated at 0 and 1. For 1D. For 2D, it would be if omega is a 2D domain, then the integral over partial omega is an integral over the boundary of that domain. So it's an integral over a line. So this is just boundary, wherever boundary is. That's why the omega and partial omega are used, because it's, in 1D, then omega is just a line and the boundary are just the 2 points. In 2D, omega is whatever 2D part, and then partial omega is basically whatever curve is around the domain. In 3D, omega is some volume. Partial omega is the surface that covers that volume. Other questions? So I know this is completely strange. This is very, very, very mathy. But we need to do it because I just do a few things to note. We need to do it because FE works directly with this weak form. FE is completely based on this weak form. And I'll give you a little bit of intuition about why is it that FE works on this. Another thing is that this weak form is completely equivalent to that classical form of the problem. Another note, why is it called weak form? It's called a weak form because of the order of the derivatives. So the original problem had a second derivative. Had basically a d squared dx squared. And instead, this problem does not have any second derivatives. At most, it has this product of the first derivative. Some ddx of something times the ddx of something. That's what makes it weak, that you don't need the higher derivatives. This has some implications for FE because it's much easier to interpolate functions that need one derivative than second derivatives. All right, any questions? I want to come back a little bit to the intuition, but not to be talking all the time. I'll give you 5 minutes to basically look at the heat transfer problem in 1D. You'll notice that it looks very similar to the elasticity problem in 1D. They look a little bit different in 2D and 3D, but in 1D they look very similar. So you can work in pairs, and then I would say just write out what the weak form is for the heat transfer problem. And I'm not gonna do the entire derivation, I will skip it at the end, but I'll give you some time to basically review what we just did, just restate it for the heat transfer problem. Maybe like 3 minutes. All right. So for that one, let me just try to see what the, so ddx, ak, just very quickly, ak the temperature dx plus s equals 0. So to go from the strong form to the weak form, we're gonna integrate and multiply by w of x. Then we're gonna do integration by parts. And I'm basically passing this derivative to the w. So I'm gonna have ddx w of x times ak dt dx only in one of the terms. So integral over the boundary of ak dt dx times w of x. And then the last one is the SW of x. So I just did integration by parts. And then the last one is to know that use boundary conditions. We have at x equal L, we have the temperature. So at x equals L, we have temperature is some known temperature. And at x equals 0, we have k d t dx equals minus q. Yes. Minus q equals q bar. So it's given us q bar. All right, so we need to use it. Remember that for this, basically we know w at L equals 0, and this we just substitute. So the weak form reads is very similar to the solids problem. So find the temperature on domain 0xL with the essential boundary condition. So T at L equals T bar, such that the integral, I'm just gonna copy. Such that this, and now here, not all of the integral, but just the part of the integral that has a flux. So typically I would use gamma q. And here, I'm just gonna have a q bar. A q bar for all w of x, with the only thing that I need of the w of x is that w at L equals 0. And that is the weak form. Any questions about that? If not, then I'll give you another 2 minutes to get this one started. Like, I'll give you 3 minutes and then I'll just write out the weak form. I won't do the derivation, but give it a go to this one, and then I'll just give you the answer just before we finish. Come to that next class. It does have a meeting. It has some information. For now, whenever you know the value of the function, this the value then you just set the wave function. So out of your two types of boundary conditions, you either know the function or you know the derivative function. If you know the function, which is this essential boundary condition or the essential boundary condition, then automatically set the wave function to 0. It has some meaning, it has some interpretation, which I'll come to next section. But for now, yeah, just set it to 0. One minute left, so I need to write out the answer. And then if you didn't get to the answer, I would say do the process and see if you get to the same answer. So it's going to be find u of x on domain with, I have essential boundary conditions for both. So u of 0 equals 1, u of 1 equals -2, such that minus the integral over omega of kappa du dx dw dx, and then plus integral over omega of minus gamma u plus 2x squared, all of that times w of x equals 0 for all, this is for all w of x with w at 0 equals w at 1 equals 0. That is the weak form for this statement. Note that the weak form in this case does not have any boundary integrals because we have Dirichlet boundary condition on both boundaries. So again, that's the final answer. I'll upload the PDF, and if you didn't finish now, I would say just try to work it out on your own and get to the same answer, and then we'll come back to this on Wednesday. See you on Wednesday.